We will encounter a number of situations in the chemical sciences where we may want to relate the change in enthalpy to the change in energy during a process. To do so, we will be able to save a lot of time by making some useful approximations if we pay attention to the physical state of the substances involved in the process. Let us first assume that the process we are studying involves only gaseous substances that follow the ideal gas law. By definition, the molar enthalpy is equal to plus P times Vm. For ideal gases, the molar volume can be written using the ideal gas law as Vm equals RT divided by P. To get an idea about the magnitude of the volume per mole of ideal gases under ambient standard conditions, let us plug in this equation 300 Kelvin and 1 bar as the values for the temperature and pressure. We use the SI unit for R equal 8.3145 joules per mole per Kelvin and obtained 0.025 cubic meter per mole or 25 liter per mole for the molar volume. Now the molar enthalpy, H sub m, can be expressed as UM plus PV sub m, hence as UM plus RT. Under standard ambient conditions, the difference between the molar enthalpy Hm and the molar energy U sub m is therefore 2.5 kilojoules per mole. Let us do a similar calculation for liquids and solids. Unlike for ideal gases, there is no simple equation of state that we can use to express the molar volume of a liquid or a solid in terms of temperature and pressure. So, we will use the relationship applicable to any substance in any phase that connects the density, the mass, and the volume for 1 mole of substance. The molar volume is the ratio of the volume V to the number of moles N. The number of moles N is equal to the mass of the substance divided by the molar mass. So the molar volume can be expressed as the ratio of the molar mass and the density. Since we are only interested in approximate comparisons of the molar volume for a substance in different phases, we will take a shortcut and assume a reasonable molar mass and density for a typical small organic molecule to calculate the molar volume. Let us consider simple organic molecules like water, methanol, or acetone. Their molar mass ranges from 18 grams per mole to 58 grams per mole. So let us take 25 grams per mole as a typical molar mass in this range. Most organic substances have densities under ambient conditions in the vicinity of 1 gram per centimeter cube. So for such substances, the molar volume will be of the order of 25 centimeter cube per mole or 0.025 liter per mole. So we conclude that 1 mole of gas occupies approximately 1,000 times more space than 1 mole of liquid or solid under standard ambient conditions. Again, the molar enthalpy is the sum of the molar energy plus the term P times molar volume. We can now conclude that the molar enthalpy is greater than the molar energy only by approximately 2.5 joules per mole. What lesson can we draw from these rough but very useful calculations? First, we conclude that when gases and liquids or gases and solids are present, we can always neglect the volume of the solids and the volume of the liquids in comparison to that of the gases. This will become very handy in calculations of work, of expansion or compression for chemical reactions and phase change. Second, we can conclude that when gases are involved in a process, the change in enthalpy and the change in energy will differ slightly from one another. RT per mole of gas. On the other hand, when gases are not present in the process, we will assume that the change in enthalpy is the same as the change in energy because the change in PV is negligible for both liquids and solids. We will return to this point in the next lecture.